In this video, we're going to investigate falling things, and we're going to ask the question, do falling things accelerate? Well, there's kids jumping off of cliffs. Do they accelerate? There's balls set to fall, released by a mechanism. Do they accelerate? There's leaves falling in autumn. As they fall, do they accelerate? And skydivers, of course, fall. As they're falling, do they accelerate? Let's find out. So we've asked the question, do falling things accelerate? What we're looking for is evidence. So in this case, what you're looking at is we use Loggerpro to record the motion of a falling object. And we recorded the distance versus time of the object, and we also recorded the velocity versus time of the object. So let's see what these graphs tell us. First of all, I can see that the velocity is not the same. The velocity is increasing. A constant velocity would be a horizontal line on this graph. So the fact that the velocity is increasing seems to indicate that it is accelerating. Definition of acceleration is the rate that the velocity changes. So it appears that the velocity is changing, and therefore it appears it's accelerating. Now on a distance time graph, we can subtly see that this line is not a straight line, but a curve. Now we're going to let Loggerpro tell us if that's really true, but I can see perhaps that this is more of a straight line, whereas that's more of a curved line. Now if I remember that a curved line means that the slope is actually increasing, and if I also remember that the slope of a distance time graph is the velocity, if the slope is increasing, the velocity is increasing, which means I'm accelerating. So actually what I have here is two pictures, curved distance time, straight increasing velocity time, two pieces of evidence that falling objects do accelerate. Now we want to ask the question, what is the acceleration rate of falling things? If they fall and we believe that they accelerate, let's get a number for the acceleration rate. So we have to remember back to the lab where the car was rolling downhill with the motion detector, and we figured out the acceleration rate of that car rolling downhill using Loggerpro. And what we did is we realized, first of all, there's two ways to do this. Way number one is to realize the definition of acceleration is the rate that velocity is changing, which in mathematics is if I have a velocity time graph, the rate that the velocity is changing is the slope. So if I could get a straight line fit on this graph, the slope of that line will give me the acceleration. Now the distance graph, a little more complicated. If I can curve fit this, a curved line is a quadratic. And if you remember from the car going down the hill lab, we were able to get a number based on this curve fit. So we're going to do that as well. Well, here's the results of Loggerpro's curve fit. First of all, I can see that on the distance time graph, Loggerpro said you indeed do have a quadratic. So it said the formula here is distance is equal to at squared plus bt plus c, right there. Gave me values for a, b, and c. So it actually said, yep, that's curved, it's quadratic. Velocity time graph, it said this is a straight line. And it said you have a formula of y equals mx plus b, or v equals mt plus b for our variables. And it calculated the slope and the y-intercept for this line. So now what I want to do is I want to use the data for the distance time graph and the velocity time graph to calculate the acceleration of this falling object. So let's use the distance time graph first. And the key is we're going to use this formula. So let's write this formula down. It said when you curve fit this, your distance was equal to a number, a, times t squared, plus another number, b, times t, plus a third number. So what it had done, and here are the numbers A, B, and C, is it literally said, here is your formula. Now the way that we can use this to calculate the acceleration is by comparing this formula to a formula in our reference tables that I'm going to write down. So our formula in our reference tables was d equals, and I'm going to write this out of order, 1/2 at squared plus v initial times t. And that's all that the formula said actually on our reference table. So actually I can add a 0 to that and it'll be the same thing. So this formula is what's on our reference tables for an object that's accelerating, and this is what Loggerpro said. So Loggerpro actually says this number a, according to your reference tables, is half of your acceleration. So let's write that down. So this number a, according to Loggerpro and our reference tables, is really half the acceleration. This sits in front of the t squared. On our reference tables, this sits in front of the t squared. So those two things must be the same thing. So the number that Loggerpro gave for a, which is right in here, is 4.879, and that's equal to half the acceleration. So the acceleration would be twice 4.879, which if I round off to 2 decimal points is 9.76 meters per second, or meters per second squared. And that means that this object that was falling had an acceleration rate of 9.76 meters per second squared, or that it sped up by 9.76 meters per second every second. Now let's use the velocity time graph to see what the acceleration rate is. So let's just write down for our reference here, the distance time graph said 9.76 meters per second squared is our acceleration rate. The velocity time graph, I have a straight line, and if you remember we said the slope of a velocity time graph, which tells me the rate that the velocity is changing, which is by definition the acceleration, the slope of this line gives me the acceleration. So the slope here, it says, is 9.76 to 2 decimal points, meters per second squared. And so directly, since this is the rate the velocity is changing, that must mean this is also the acceleration. So my distance time graph gave that as the acceleration of this object, and my velocity time graph actually totally agreed with it and gave me the same number. Well, after dropping many things throughout human history, scientists have determined that the acceleration due to gravity, we got 9.76 meters per second squared, but the accepted number, which is on the front page of your reference tables, is 9.81 meters per second squared. So falling things accelerate, which means their speed goes up by 9.81 meters per second every second.